This is the video 3 of MEKG video series. In this video, instrumentation and control topics are discussed. Topic 1: Intrinsically safe equipment.
In this media, you will learn about intrinsically safe equipment. Intrinsically safe equipment do not promote ignition of the explosive mixture. This can be done by placing a Zener barrier in the electrical circuit. Thus, the high voltage to the hazardous area is reduced by the Zener diodes, whereas the maximum current flow is limited by the resistors. Intrinsically safe systems have very low energy level, so they can be used only in the instrumentation and control circuits in the hazardous areas. Thus, you have learned about the intrinsically safe equipment.
Topic 2: Flameproof equipment.
In this media, you will be able to learn about flameproof equipment. During the ignition of a flammable mixture, high pressure is developed. A flameproof enclosure has the capability to withstand this pressure. This is done by cooling the products of explosion down below the ignition temperature. The hot gases are allowed to escape through the gap between the flanged joints. This path should be maintained properly. The bolts must be checked and tightened properly. Painting, corrosion, and obstructions in the gaps should be prevented. Thus, you have learned about flameproof equipment.
Topic 3: Pressurized or purged equipment.
In this media, you will be able to learn about pressurized or purged equipment. An enclosure is made air-free under this technique. This can be done by either pressurization or purging. Under pressurization method, the enclosure must be maintained at an overpressure of 0.5 mbar relative to the atmosphere. In the case of a purged enclosure, purging gas is continuously supplied into the enclosure. Purging gas can be either air or any inert gas. Thus, you have learned about pressurized or purged equipment.
Topic 4: Liquid level gauges.
In this media, you will learn about the liquid level gauges. Every LNG tank must be fitted with a liquid level gauge. The classification of gauges as per the IMO codes is listed as below. 1. Indirect systems. Example: weighing or pipe flow meters. 2. Closed devices without contact. Example: ultrasonic or radioisotope sources. 3. Closed devices with contact. Example: float gauges, bubble indicators, and so on. 4. Restricted devices. These devices penetrate into the LNG tank and release small amount of liquid or vapor. Example: fixed or slip tube gauges. Thus, you have learned about the liquid level gauges.
Topic 5: Float gauges.
In this media, you will learn about the float gauges. Float gauge is a commonly used device in most of the tankers. Float gauges can only record liquid level greater than 4 inches. The float gauge consists of a float. The float is connected to an indicating device by a tape. This enables local and remote readout in the float gauge. The float gauge is also provided with a gate valve. This allows the isolation of the float gauge so that it can be serviced in a safe environment. The float should be taken out from the liquid level when not in use. Continuous exposure to the fluctuation in level can damage the tape tensioning device. Thus, you have learned about the float gauges.
Topic 6 Nitrogen Bubbler Gauge.
In this media, you will learn about the nitrogen bubbler gauge. The LNG tank is mounted vertically with a small bore tube. This is the nitrogen bubbler gauge. Nitrogen bubbler gauge consists of a tube with a liquid. Nitrogen bubbler gauge determines the pressure required to displace the liquid from this tube. Nitrogen is passed through this tube so that it just begins to bubble at the bottom. The prevailing pressure is the function of liquid density and liquid level. If the density of the LNG in the tank is known, the pressure reading can be obtained directly. Otherwise, the density of the LNG is calculated by placing two such tubes side by side with known vertical distance. Thus, you have learned about the nitrogen bubbler gauge.
Topic 7 Differential Pressure Gauge.
In this media, you will learn about the differential pressure gauge. Differential pressure gauges can be used in ships only if the tank is above the deck. Inert gas is passed through the signal lines of this device. This gauge works based on the differential pressure between the vapor and liquid. Thus, you have learned about the differential pressure gauge.
Topic 8 Capacitance Gauge.
In this media, you will learn about the capacitance gauge. Capacitance gauge consists of two probes. When immersed in LNG liquid, it determines the change in the electrical capacitance between them. The probes are placed in an open protective tube. The liquid content at all levels throughout the depth of the tank can be determined by the extension of this tube. Sensors can be fixed horizontally at the required levels for enabling a high-level alarm. This device comes under the category of intrinsically safe device. This device should be maintained dirt-free to avoid inaccuracies. Thus, you have learned about the capacitance gauge.
Topic 9 Radar Gauges.
In this media, you will learn about radar gauges. Radar gauge is a type of tank gauging equipment. As the name suggests, this device works under the principle of radar. Radar-type liquid-level gauges have been specifically developed for LNG tankers. Radar gauges work under very high frequencies of about 11 GHz. Thus, you have learned about radar gauges.
Topic 10 Level Alarm and Automatic Shutdown System.
In this media, you will learn about level alarm and automatic shutdown systems. An independent high-level sensor must be compulsorily fitted in every LNG tank except Type C tanks. The sensor should have the ability to give an audible and visual alarm. They must also have the capability of automatic stopping of the LNG flow into the tank. These independent high-level sensors can be of float, ultrasonic, or capacitance sensors. If the valve stopping the LNG flow shuts quickly, there is a chance of high rise in the pressure. Thus, you have learned about level alarm and automatic shutdown systems.
Topic 11 Pressure and Temperature Monitoring.
In this media, you will learn about pressure and temperature monitoring. As per the IMO codes, pressure must be monitored continuously throughout, in various components of the LNG system. Pressure switches are also fixed to various components, so that these switches act as alarm or shutdown units. As per the IMO codes, the temperature gauges should be fixed both at the bottom of the LNG tank and also near the top of the tank. The position of the gauge at the top of the tank should be below the highest allowable liquid level. The temperature gauge should be marked with the allowable lowest temperature level of the tank steel. In the case of Type A tanks carrying LNG below -55 degrees Celsius, the position of the temperature gauge differs. Here, the gauge is positioned either within the insulation or on the hull structure near the LNG tank. Thus, you have learned about pressure and temperature monitoring.
Topic 12 Gas Detection Systems.
In this media, you will learn about gas detection systems. One of the important codes of the IMO is to have gas detection system fixed in all ships. These systems must be connected to proper audible and visual alarms in the control room. The detection system must be located in the following areas: LNG tank room, electric motor rooms, LNG control rooms, unless classified as gas safe, enclosed spaces excepting spaces containing Type C LNG tanks, airlocks, vent hoods, and gas to ER supply ducts. The gas detection heads should be subjected to regular testing and analysis. Sampling for each detector head should be done within an interval of 30 minutes. A normally functioning detector head activates the alarm when the vapor concentration reaches 30% LFL. At least 2 sets of portable gas detection equipment should always be readily available in the ships along with oxygen measuring equipment. All personnel in the ship should be given training on the usage of gas detection equipment along with the manufacturer's instructions. Thus, you have learned about gas detection systems.
Topic 13 Toxicity Detectors.
In this media, you will learn about toxicity detectors. Toxicity detectors are used to determine the amount of toxic gases in a sample. The instrument consists of a sealed detector tube. To use this instrument, first the ends of the sealed tube are broken. Then, the detector tube is inserted into the instrument and the gas to be sampled gets absorbed into it. Now, the color of the gas in the tube changes as the result of the reaction between the toxic gas and the chemicals inside the tube. The color stain raises against the scale reading marked in the tube. This reading gives the amount of toxic gas in the sample in terms of parts per million, ppm. The detector tube has a specific shelf life stamped on it. It should be used before that date. Before inserting, the tube should be checked for any leakage. Thus, you have learned about toxicity detectors.
Topic 14 Oxygen Analyzers.
In this media, you will learn about oxygen analyzers. This is the diagram of an oxygen analyzer. In this oxygen analyzer, the oxygen diffuses through a Teflon layer. This diffused oxygen mixes up with the potassium chloride solution. This process of mixing activates the chemical cell. Current flows around the circuit when the switch is on. The current flow around the circuit can be checked through the deflection shown by the ammeter needle. Current flow increases on the increase of oxygen absorbed by the solution. The ammeter needle indicates the oxygen percentage in the atmosphere. This oxygen analyzer is insensitive and doesn't need a battery to operate. Other oxygen analyzers, such as polarographic and paramagnetic oxygen analyzers, are more sensitive and need batteries for operation. It is very risky to change the batteries in the gas dangerous zone, and it is not recommended. Oxygen analyzers have dual scales. Both of these scales have separate functions. This diagram shows the schematic diagram of a polarographic cell used in oxygen analyzers. In polarographic cell, the electrochemical reaction at the permeable membrane controls the current. A polarographic cell has a lifetime of about 6 months when operated consistently. Thus, you have learned about oxygen analyzers.
Topic 15 Catalytic Instruments.
In this media, you will learn about catalytic instruments. This diagram shows a basic electric circuit, Wheatstone bridge, of a combustible gas indicator. The sensor filament of the combustible gas indicator sucks the gas. The sucked gas gets heated by the bridge current and burns catalytically. Even if the gas has a lower flammable limit, the gas burns on the filament surface. This process raises the temperature of the filament, resulting in the increase in electrical resistance. The increase in the electrical resistance unbalances the bridge. This imbalance indicates the amount of hydrocarbon content in the air. Catalytic instruments indicate flammability, and the catalytic instruments can also be used to find the presence of gas in air. The meter scale present in the instrument can read from 0% to 100% of the lower flammable limit. The batteries contained in these instruments must be checked before use. Checking the instruments using a calibration gas at frequent intervals is a recommended practice. The instrument manufacturers provide a calibration graph for the instruments. The meter readings should be within the range indicated on the calibration graph. This type of meter shows a low or even zero reading for the tank spaces containing atmosphere above the flammable range. When the sample is detected by the meter might show a momentary strong deflection, but after that it comes down to steady, low or zero. The steady reading can be misleading, and hence the momentary deflection must always be considered important. The momentary deflection can also be an indication that the gas being sampled is above the lower flammable limit. Certain instruments also have sensor filaments. The presence of other gases, like halogenated hydrocarbons, may spoil the catalytic action of such sensor filaments. Digital gas analyzing instruments are also available in the markets. The batteries contained in these instruments should be charged only in gas-safe areas. Thus, you have learned about catalytic instruments.
Topic 16 Multipoint Flammable Gas Monitors.
In this media, you will learn about multipoint flammable gas monitors. The main function of catalytic indicators and heated filament flammable gas indicators are for testing LNG tanks, enclosed spaces, and void spaces. These indicators are portable instruments that are used while performing gas-freeing operations. For spaces such as compressor rooms, machinery spaces, LNG holds, and motor rooms that are air-filled or air-ventilated, catalytic instruments are used in multipoint form. Catalytic instruments are installed on ships' bridges or in LNG control rooms in the multipoint form. The installed instruments take samples from the points under surveillance. The instrument monitors and gives alarm on detecting a low percentage of LFL, lower flammable limit. The catalytic type doesn't function at the void spaces that are inerted frequently with nitrogen. In such cases, an infrared analyzer is used as the central multipoint instrument. This diagram illustrates the principle of an infrared analyzer. For absorbing the infrared radiation, this multipoint instrument employs the property of hydrocarbon gas. The two nickel or chrome emitters encased within the instrument send infrared radiation to the two separate channels. Infrared radiations are sent through a reference cell free of hydrocarbons and a sample cell. A semicircular beam chopper driven by an electric motor alternatively blocks the two channels. The radiations transmitted from the channels pass through the detector cell. The radiations received by the detector cell heats the gas. The sensitive membrane of a condenser microphone detects the resultant rise in pressure. Because of the chopping of two beams and the absorbing effect of hydrocarbons inside the sample cell, the output of the microphone is an alternating current. This alternating current is amplified and recorded. The alarm is activated when a gas is detected. Thus, you have learned about multi-point flammable gas monitors.
Topic 17 Coriolis Mass Flow Meter.
In this media, you are going to learn about the Coriolis mass flow meter. It consists of two parallel tubes, one driver, and two sensors. Driver is used to give mechanical vibration to the tubes. It consists of two brackets, namely A and B. Bracket A has one magnet fixed to it. Bracket B contains a coil, supplied by 50 Hz supply. Bracket A and B are relatively movable. Each sensor consists of a magnet and coil. Sensor magnets are connected to bracket A and coils are connected to bracket B. When an alternating supply is given to the driver coil, it attracts and repels the magnet as the cycle changes. This will cause relative movement between brackets. Due to this relative movement of brackets, the flux linking with coils in the sensor changes. This change in flux linkage causes induced EMFs in the sensor coils. When there is no flow in the tubes, mechanical vibration produced by the driver is identical at two sensing points. Due to this, induced EMFs produced in the sensor coils are same. So, the difference in these EMFs is zero, and it does not produce any output in the meter. Now, consider the fluid is flowing through the tubes. Because of vibration generated to the tubes, the fluid inside of the tubes will produce an inertial force. This inertial force, or Coriolis acceleration force, produced in the fluid depends on mass flow rate of the fluid. This additional inertial will cause different induced EMFs in two sensing coils. So, the difference in these EMFs will not be zero, and this voltage is graduated in flow rate in the scale of the meter. In this way, we can measure the mass flow rate of the fluid. Thus, you have learned about Coriolis mass flow meter.
Topic 18 Controller Action.
The two-step automatic controller has two outputs, on or off. The correcting unit, a valve, has two positions, open or close. Consider the case of tank level control, where the water level in the tank is maintained at a desired level. When the water level increases above the desired level, the level sensor sends a signal to the controller which closes the valve. When the water level decreases below the desired level, the level sensor sends a signal to the controller which opens the valve. In this type of control, the controlled condition oscillates. As you observe in the graph, the water level in the tank keeps oscillating above or below the desired level. Proportional control eliminates the oscillations which occurs in on-off control. The valve can be adjusted to infinite number of positions between its maximum and minimum limits. The controller output is directly proportional to the deviation between the controlled condition and the desired value. The opening of the valve will depend on the extent of increase or decrease of water level from the desired level. As you can observe in the graph, when the load changes, value of the controlled condition obtained in a steady state differs from the desired value. This difference is known as offset. Offset can be reduced by increasing the gain or sensitivity of the controller. This will lead to oscillation or surging, which is also called hunting. In this control, the recovery time to achieve the controller condition is high. The problem of offset and hunting can be overcome by adding integral action to a proportional controller. The addition of integral action causes the output of the controller to change at a rate proportional to the deviation between set value and measured value. When the effect of the integral action is more, the controlled condition overshoots and tends to oscillate. When the effect of the integral action is less, it takes a longer time to achieve the controlled condition. Correct application of integral action will have a slight overshoot, but the controlled condition is achieved quickly. Derivative control stabilizes the control system and allows the reduction of offset or shorter integral time. The controller output signal is proportional to the rate at which the error is changing and not upon the value of error. The derivative action is greater with the shorter derivative action time. This is the reverse of the integral action time, where shorter the time, the greater the effect. When compared with the other control actions, P plus I plus D control action reduces offset and takes a shorter recovery time to stabilize the system.
Topic 19: Temperature Control System Split Range Control.
You can see the schematic diagram of a split range temperature control system installed on board. It controls the temperature of jacket cooling water circulated inside the main engine. This system has a sensor which measures the temperature of water and an automatic controller which regulates the temperature of the water. The sensor monitors the cooling water outlet temperature and sends a signal to the automatic controller. The controller compares it with the set value and sends the signal to both the valve positioners. The automatic controller output to the valve positioners ranges from 0.2 to 1 bar. When the cooling water temperature is less than the set value, the controller output will be in the range of 0.2 to 0.4 bar. The steam heater valve opens and maintains the set temperature. When the cooling water temperature increases, the controller output ranges from 0.5 to 1 bar. The cooling water valve of the cooler opens and the set temperature is maintained. Control signal ranging from 0.4 to 0.5 bar is called the dead band. It ensures that both the valves are not open at the same time. In this way, the control system regulates the change in jacket water temperature of the main engine.
Topic 20: Temperature Control System Cascade Control.
You can see the schematic diagram of a Cascade control system installed on board. In this system, there are two controllers connected in series, a P plus I controller, which is the master controller, and a P controller, which is the slave controller. The two measuring elements in this system are the primary measuring element and the secondary measuring element. The primary measuring element detects the change in jacket water outlet temperature and sends the signal to the master controller. The master controller compares the primary measured value with the set point and sends the difference value to slave controller. The secondary measuring element detects the change in jacket water cooling inlet temperature and sends the signal to the slave controller. Depending on the error between the master controller output and jacket water inlet temperature, the slave controller generates an error signal. The error signal is fed to both the steam control valve and cooling water control valve. The dead band ensures that both the valves are not open at the same time. When the outlet temperature is above the set point, the cooling water control valve is opened. The seawater cools the jacket water flowing through the cooler up to the set point. If the outlet temperature is below the set point, then the steam control valve is opened. Steam entering into the heater increases the temperature of jacket water up to the set point. In this way, the control system regulates the change in jacket water temperature of the main engine.
Topic 21. Automatic Combustion Control System.
You can see the schematic diagram of an automatic combustion control system used in a boiler plant. This system has four measuring elements. A steam flow sensor, which measures the flow rate of steam in the boiler. A steam pressure sensor, which measures the pressure of steam in the boiler. A fuel flow sensor, which measures the fuel flow in the boiler burner. An airflow sensor, which measures the air to the boiler. The two controllers in this system are a fuel flow controller, which regulates opening and closing of fuel valve. An airflow controller, which regulates the airflow by opening and closing of dampers. The steam pressure and the flow signals are transmitted to a computing relay. The computing relay generates the master signal depending on the load of the boiler. This master signal represents the fuel requirements to the boiler. The master signal is fed at a set value to the low and high signal selectors. In the low signal selector, the master signal is compared with the signal representing the airflow. The selector passes the master signal only if it is lower. In the high signal selector, the master signal is compared with the signal representing the fuel flow. The selector passes the master signal only if it is higher. When the steam demand is high, high signal selector passes the master signal to airflow controller. The airflow controller increases the airflow by adjusting the damper position. As the airflow increases, the airflow sensor transmits the signal to the low signal selector and airflow controller. The master signal passes to the fuel flow controller to increase the flow of fuel by adjusting the fuel valve position. If demand is low, the low signal selector permits the master signal to pass to the fuel flow controller. Fuel flow controller decreases the flow of fuel by adjusting the fuel valve. As the fuel flow decreases, the fuel flow sensor transmits the signal to high signal selector and fuel flow controller. The selector sends the master signal to the airflow controller to decrease the airflow by adjusting the damper. In this way, the control system maintains the air-fuel ratio and prevents incomplete combustion of fuel with changing steam demands.
Topic 22. Two-step on-off control.
A two-step automatic controller has two outputs, on or off. The correcting unit, a valve, has two positions, open or close. Consider the case of tank level control, where the water level in the tank is maintained at a desired level. When the water level increases above the desired level, the level sensor sends a signal to the controller, which closes the valve. When the water level decreases below the desired level, the level sensor sends a signal to the controller, which opens the valve. In this type of control, the controlled condition oscillates. As you observe in the graph, the water level in the tank keeps oscillating above or below the desired level.
Topic 23. Pneumatic control system.
A nozzle and flapper arrangement transmits the pneumatic signals in a pneumatic control system. Air is fed to the nozzle at a constant pressure of 1.5 to 2 bars through a restrictor. The function of a restrictor is to limit the airflow. When the gap between nozzle and flapper is minimum, the outlet pressure from the nozzle is maximum. When the gap between nozzle and flapper is maximum, the outlet pressure from the nozzle is almost equal to the atmospheric pressure. The curve shows the relationship between outlet pressure and flapper-nozzle gap. The curve is linear only over a certain range. In this range, the pressure varies proportionally with flapper-nozzle gap. The sensitivity of this arrangement is decreased by adding a negative feedback below, which reduces the flapper movement for a given input range. The output signal is fed back to the flapper through a below. It is termed negative as it moves the flapper back towards the original position. If the flapper is moved further away from the original position, then it is called positive feedback. The output from the flapper-nozzle arrangement is small. It cannot be transmitted over long distances and cannot operate large equipment. Hence, a booster relay is used for amplifying the output signal. Air is supplied to the booster relay. When there is no output from the nozzle, the valve spindle opens the exhaust air passage and most of the air supplied leaks off. When the nozzle output is maximum, the valve closes the exhaust air passage. The supplied air comes out of the relay at high pressure of 1.5 bars. Thus, an increase in output from the nozzle results in an increased output signal from the relay. The diagram shows a simple proportional controller with booster relay. A set value of pressure, P sub S, is fed in one below. The measured value of pressure, P sub M, is fed into the opposite below. The measured value of pressure, P sub M, will be proportional to the measured variable. The variable can be temperature, flow, and others. Any difference in these two pressures, P sub M and P sub S, causes movement in the lower end of flapper, varying the output pressure. The output of the unit is proportional to the difference between the set value signal and measured value signal. The problem of offset in proportional controller is overcome by introducing an integral bellow opposite to the proportional bellows. A variable restrictor is placed before the integral bellow so that the integral action time can be varied. Additional integral bellow will introduce a positive feedback to raise the pressure P2 at a rate dependent on the deviation. Integral action will continue until the deviation ceases and there is no offset. Derivative action is obtained by placing a variable restrictor before the proportional bellow. This gives a faster response as the output is proportional to the rate of change of deviation. Derivative action has a stabilizing effect on the system and reduces overshoot.